So good afternoon, everybody. It's a pleasure to be back for my next lecture, Gresham lecture, the last one of the current academic term. And today I'm going to talk about the Dark Ages, but the Dark Ages from a point of view that may be a little strange to some of you, because this will be the Dark Ages of the universe, where there really is a Dark Ages, and which represents the era that we cannot see directly, where there were no stars. But it's critical because if we want to understand our beginnings, the traces are there, and we have to explore them somehow. Okay, so cosmology is the study of the universe, and we've made enormous progress in this field over the past few years. It's become a precision science. That's the big change. People have wondered about the universe and its contents and its origin for a very long time, but maybe at the turn, early in the 20th century, Einstein made a huge contribution with general relativity, which contained the tensor calculus, and this made a big difference because suddenly it was the experts only who could understand the cosmology and join the debate, and ever since then, the scientists have jumped in with their experiments, and it's become very much a question of precision of the details now to try to understand the missing links. So what are these missing links? Well, they're unfortunately rather significant. We don't know what the universe is made of. We call this the dark matter. We're looking for it. We haven't identified it. We don't know the major content in the energy of the universe, called dark energy, which is responsible for acting against gravity, accelerating the universe. We don't know what that is. We see it at work, but we're trying to understand it better. But above all, and what I'm going to mostly focus on in this talk, is the beginning. Where did we come from? And we have a wonderful theory developed in the 1980s, which tells us a lot about where we came from. And we're trying very much to understand and test this theory. It's all right to have a theory of something, but it's no good unless you can prove that it's true. And the trouble with theories in science in general is you can never be really certain something is true. What you can do is show that it's very, very likely. You can believe in astrology, for example. That you can show that is highly unlikely, but that doesn't stop some people believing in it. We try to do sort of the opposite in science. We try to show things are very likely and give people confidence. So inflation then, this is sort of a picture of our understanding of the universe. So here we are today, and this was the beginning, and it's deliberately made very fuzzy because there's a big question mark because we have no theory of what happened at the very beginning. But then our theories begin with this epoch of incredibly rapid expansion called inflation. And we can actually see back with telescopes to this first period, the end of this inflation period really, some 300,000 or 400,000 years after the Big Bang. Before then it was too dense to really see very much. And this is the microwave background, and we measure the seed fluctuations on this with telescopes in space. And ever since these seeds, these ripples in space grow into structures which make the galaxies, and one of which we live in, the Milky Way galaxy. Okay, so here's where the stars first appeared. And before then, we call that the Dark Ages. And before then, there's a big fog and we can't really see back any further. But the inflation does tell us that things did begin at a very specific instant in time, very close to time zero, projecting backwards from now. So how do we actually understand more about that? So let me just show you a slightly blown up view of the Dark Ages. Okay, so here we are. This is 400,000 years after the Big Bang. And we see in this fuzz on the sky, seen with microwave antennas, it's been said that if you turn your television in between stations, you see a fuzz on the screen, it's out of tune. And 1% of that fuzz on the screen is the glow from the early universe, seen in microwaves, and discovered in the mid-20th century. Anyway, the tiny changes in strength, seen as fluctuations, are what we see now as proofs of that there were structures from which all structure began, fluctuations, seeds, if you like. But before those stars first appeared, in the middle of this picture, you have a period when nothing was there, just darkness. And we have to understand the building blocks from which galaxies were made. There were clouds of gas that are not glowing. And we're trying very much we're trying to push back in time to get as close as we can to the beginning. Okay, so what are these challenges that we have before us? So one of them is to understand the building blocks from which galaxies made, these gas clouds from which the Milky Way assembled and all other galaxies around us assembled. Another one is to find an imprint from the beginning. So when the universe underwent this incredible expansion from very, very early on, which we call the inflation theory, there was a lot of shaking around in this rapid expansion, which led to things called gravity waves. Now, gravity waves basically are just like electromagnetic waves, except they're produced by changing the gravity field, and they've been measured recently by specialized antennas. They're a prediction of Einstein's theory that they should be seen, and we've seen them due to stars, actually, merging black holes, actually, stars that turn into black holes and then merge together. When you form a black hole, you get a burst of gravity waves that was discovered just a year ago, predicted 100 years before by Einstein. And there should similarly be something imprinted from the beginning of the universe. Now, unfortunately, the universe expands so much, so these gravity waves from early on, which may have been very high frequency at the beginning, get slowly, redshift expanded with space. Their frequency goes down and down and down. Very hard to measure, but they leave a signature, a twist on the microwave background fluctuations, which we're searching for. Haven't found them yet. And finally, what I'm going to talk about later, and I'll explain exactly what I mean by this, is that these fluctuations not only have this gravity wave twist on them, but they also have something else, which I'll explain what that is, non-Gaussianity, non-randomness basically, and that's an imprint also of the very beginning. So if we can actually measure any of these three things, that would take us back further. The building blocks before the first stars, clouds of gas, and these other two imprints would actually tell us about the very, very beginning, how inflation occurred, whether inflation really did occur. It's just theory. Okay, so the building blocks. So in this cartoon, you can see how structure, today at the bottom, was assembled from many smaller things. Okay, so this hierarchy is how structure forms in the universe. Today, we measure the large-scale structure, the assembly of galaxies, many galaxies, big ones, the Milky Way, others. Then there are lots of small galaxies around, and these are thought to be the building blocks of the bigger ones. But where all the galaxies came from was even smaller building blocks, gas clouds, which were there a long time ago, and they're predicted by the theory of the nature of the dark matter. And so, and there should be lots of dense clumps in the matter distribution, which were there from very long ago, okay? Clumps, gas clouds. And these can't be seen today because they've all assembled into galaxies, but if you could look back in time, with telescopes that can actually look at things very far away in the universe, powerful enough telescopes, then you can hope to see these direct clumps. And so here is, for example, a cartoon of such clumps. I see here that the universe is now thought to be full of inexplicably dense clumps. Someone reading the newspaper. Okay, right, so this is what we're looking for. So how do we go about this in the real world of astronomy? So we have this beautiful radiation, the microwave background from the beginning, with these tiny fluctuations embedded in it, which are the seeds of structure. We study this, and so we can, by measuring the variation on the sky of these ripples in the radiation, slight variations in temperature from place to place in the sky, we can understand the origins of where the structure of the universe comes from. Okay, so that's good. That takes us back to 400,000 years after the Big Bang. We're seeing the origins of large-scale structure, but we'd like to understand where everything comes from, and we know the building blocks of big galaxies are small galaxies. So we have things called dwarf galaxies, and they're also, many of them are very old. They're relics from the beginning. Many of them were assembled into bigger things, but a lot are left over, and those we study too. They're like fossils, basically, from the early universe. And then finally, the most mysterious thing of all, which can take us back to really the beginning, the first year of the Big Bang, is the following. It's the fact that the Big Bang theory predicts this perfect black body, okay? And we measure this, okay? What's amazing is this is an experiment which was actually done in 1990 by a satellite called the Kobe satellite. And the blue curve is a black body curve, and these red lines are error bars, but they're multiplied by 50. And if anyone has ever seen error bars, this is the most amazing, demonstration the universe was once a perfect furnace, measured in the sky. Okay, but if this picture is true, that there really are all sorts of smaller building blocks out there early in the universe, and they should leave some imprint. You shouldn't have a perfect black body. Now, if you go back early enough in the universe, before the first year basically, it was so dense, so hot, that it was the perfect furnace. But as the universe expanded, then you could expect to see slight deviations from this perfect black body radiation. And so this experiment is being designed to look for just that, to look for tiny, it hasn't been seen yet. But this, if we ever do this, and if this experiment gets approved, it finds something that will just get us back to 1 year after the Big Bang, which is amazing, because right now we can see back to 400,000 years. And so we can go back much, much closer. But what we'd like to do is probe the first fraction of a second after the Big Bang. And that gets us back to the story of the gravitational shaking of these microwave background, this tiny distortion you might imprint on it. So here is a picture of what those distortions might look like. And getting to this point is what's been called the ultimate goal in current cosmology. I'll try to persuade you that one can do even better in a moment. But basically, this sphere in the middle is a picture of the microwave sky, and you can see tiny hot spots and cold spots in these fluctuations. And those are the seeds from which all our structure formed. And then what we'd like to do is to have a much more precise look at these fluctuations, look for tiny twists due to the imprint of the shaking of the universe in the first, wait for it, 10 to the minus 37th of a second. A trillionth of a trillionth of a trillionth of a trillionth of a second after the beginning. That's when inflation occurred, and it would leave these weird distortions. So this is the distortion on the right of the gravity waves, and there's another one which comes from stuff in between, which you have to get rid of just from the effects of dark matter, which is a real problem. So it's like driving along and having a very dirty windshield trying to see the road. This stuff is hidden, but we hope to do that in the next few years. And so there are many experiments. I showed you one of them. There's a Japanese experiment too being prepared for launch in 2022. And there are all sorts of other experiments to look for this. One could do some of this from the ground. And we have experiments at the South Pole. Why the South Pole? Because there's so little water vapor in the air, it's so cold, that it's really transparent to the microwaves. And so that's a good place to go to look for these subtle effects, or in space, which is much more expensive, of course. And then Atacama Desert, another very high area where they're building telescopes, and on high-flying balloons. Okay, so all these will happen in the next 10 years to look for these tiny twists. But the problem with all of these experiments is that we're looking for this weird thing, which is called the B mode. And you can say, is there any guarantee to be or not to be? And the trouble is, the theory of inflation does not predict a definite signal to look for. It could be there. If we're lucky, we'll find it. If we find it, it'll be proof we went through this incredible expansion, a tiny fraction after the beginning. It'll give us immense trust in this theory, but it may not be there. Okay, so I'm going to tell you a much more about a much more risky strategy, but one much more futuristic. But I think it's the only one we can really think of now if we really want a definite answer. And this is going in a different direction totally from developing telescopes to look at microwaves. I'll show you that it's something totally different. And the idea is that you want to look for patterns on the sky in the microwave radiation that are just non-random. So we call this, in the end, if you shake enough things up in a box, it always looks totally Gaussian, totally. There's no particular pattern that that emerges is just random chaos. But if there is any imprint from this early theory of inflation, there should be a slight element of non-randomness, and that's what I want to try to explain to you. Okay, and so the problem is that inflation then has this prediction of very, very weak gravity waves, but there's a generic prediction which is this non-randomness, which you call non-Gaussianity. And there's always got to be some. And you can sort of understand that in a simple way because, you know, if I take some function that's totally random in physics and I do a bit of algebra on it, I square it, then it turns out then to look very different from random. That's one example, one simple example. But I'm going to show you more specifically one or two pictures, okay? So this is an element, this is what I mean by this. So this is the same, this is a simulation of the universe, okay? Large chunk of the universe, as you'd see maybe in the galaxy distribution, for example. And so this is based on what we actually observe. So the one on the left then is the real structure of the universe, okay? Very close to observations. And the one on the right is taking exactly the same model, but mixing it up, okay? So you randomize it completely, okay? And you get the one on the right. So if you like, the strength of all the fluctuations is exactly the same in the two pictures. It's their phases that are different. And so, in other words, it's the difference from randomness that is essential to our being here, okay? Now this is, in fact, the universe as it is today, more or less. But it's clear that we live in a very, you know, if things were random, we'd all be basically dissolved into, you know, into just chaos. But that's not the case, you know, in most parts of the world anyway today. So, right, so you can say the left is our universe, the right is not, okay? So let me show you another example of one of the problems in this field. So this is, again, a picture of the microwave background, the fluctuations that were discovered. This also, you know, looks at first sight non-random, okay? And I'm going to show you a very simple example of the non-randomness in this picture, which is totally a result of all the messiness in our galaxy, the dirty windshield effect. And so what I want you to look at is this particular area, and I've blown it up over here, and you can see the letters SH, right? If you look at that very carefully. Okay, you can see the H more clearly, right? Okay, so this clearly is not the initials of Stephen Hawking, but nevertheless, it's the problems that you have in trying to extract some signal that must be underlying all of this. This is some artifact of the dust in the galaxy and many other things, instrumental noise, and so we somehow have to get beyond this, okay? And it's very, very hard with the microwave background, I want to show you why that is. So what can we do then to try to do better than dealing with this messy picture? So the idea is that we're looking for a signal that's a very small fraction of the total signal, but sort of like a twist to it, basically, a twist that's much weaker even than gravity waves. And so we express all of this into some number. So I called it this number over here, this parameter over here. It doesn't matter what it is, but what I want to tell you is that we measure something for this. We set limits on it today with the microwave background, and that limit is less than 10. But to really test our theory, we have to improve that number by 1,000. And we have to go down to, not from 10, but to something like 0.01. So that's 1,000 times improvement, which is a huge effect in precision in any experiment in cosmology. We just are searching desperately for ways to do this. And it will be impossible with any experiment we can conceive of using the microwave background of the universe. I'll try to explain why that is. So we have somehow to go beyond looking for these gravitational waves, and we somehow want to improve on the microwave background satellites. Planck is the name of the last one that has the most beautiful results on the sky. We have to do 100 times or more better than that. Okay, so how can we think of doing much more precision cosmology in the future? Well, the first thing you have to realize is that the microwave background is very limited. So if you consider how many patches on the sky you can look at with the telescopes we have before you run into these irretrievable problems of the signals being contaminated completely, you have at most 1 million different patches on the sky. You're limited to that completely, okay? And so And what is more, all these patches on the sky are on the, or in this map I showed you, which is a map, it's like a surface of the universe, you know, as we see 400,000 years of the Big Bang. I showed you that sphere with the fluctuations on. So it's not even a three-dimensional thing, it's projected on the sky. And so we're looking at 1 million patches on the sky. And if you ever try to do any statistics, you know that you're just limited by random variations. And with a number of 1 million, then the most you can ever do is 0.1%. It's you take the square root of that number, and that gives you the fluctuations from place to place in the sky. And so numbers like that, so you can never ever do better with the microwave background than with this sort of, because of this problem of just your limited sampling on the sky. They're just, you just cannot basically get enough different patches on the sky. Okay, so the question really is, how do we do better? Okay, so one of the big hopes of the next few years is to use galaxies. And so the beauty of galaxies is that because they have distances from their redshifts, basically, you can slice the universe up into different shells, looking further and further away. So you can work in 3 dimensions, basically, whereas the microwave background is just something on the sky that you can see. Okay, so you can work, that means you have much more power. And you can basically, in the future surveys we're talking of, they will maybe measure 1 billion galaxies or something. And so that takes you up in this number of independent patches on the sky from 1 million to maybe 1 billion, okay? But that's maybe a bit over-optimistic because the galaxies are a bit messy, so we think maybe more realistically you can win by 100 with n, which is good. But this is not good enough because at the most, because things only work as the square root of whatever number you're increasing things by, you can win a factor of 10, which is not enough to go. So what you have to do now is to go back to these building blocks, okay? Long before we formed over here, there were all these clouds of gas way back when, in the Dark Ages, before any stars had formed. And so the question is, how on earth can you go back and study that part of the universe? This is before stars, by definition, what we mean the Dark Ages. After the Big Bang, after the radiation, cooled down, allowed the matter to start clumping, it first made clouds, the clouds assembled to galaxies, and then made stars. So you have to, because telescopes take you back in time, the further back you can look with a big telescope goes back in time towards, the few 100,000 years after the Big Bang, you can sample, in principle, these areas where there's nothing. But how do you sample them if you can't see light? What do you look at? So there's one thing you can look at from hydrogen, which is a very powerful test of the universe. And this is a property of atomic hydrogen. So atomic hydrogen basically is just a proton plus an electron, and the electron has a certain structure in its levels. And if I can have collisions between hydrogen atoms, the electron in these levels, I've indicated schematically a transition from one level to another level, and this transition corresponds to a wavelength of 21 centimeters. Okay, and we study hydrogen everywhere in the universe, in our galaxy, in the Milky Way, by doing radio astronomy at 21 centimeter wavelength, which is 1400 megahertz or so about, basically. Okay, so what are you going to do? And these electrons are excited by collisions. They go from one spin to another spin, and when the thing then, the hydrogen then stays there for a while, the electron comes down again, emits energy, and you can see emission. And if there's some background radiation, then that can excite the electron, and you take out energy at this particular frequency, you get absorption. So this is how we map things far away with hydrogen. Okay, so this is what you want to do. You want to basically look for hydrogen clouds, and you're going to look for the effect of there being the microwave background, basically going through this hydrogen and taking out a tiny bit of the microwave background radiation, which causes the jump of the electron and gives you a black spot effectively in the background, which is the very, very exact frequency of the energy level difference. And so because you're measuring, this happens at a very precise frequency from the quantum theory, very precise wavelength, because between then and now, there's a certain expansion of the universe, it gets redshifted, you know exactly when this would have occurred. So that's sort of the idea in principle. Okay, sounds all miraculous, but let me show you the way this works for hydrogen as it really is in the universe. So this schematically shows you the temperature of the radiation, which now is seen as microwaves, at 3 degrees Kelvin. Okay, that's the perfect black body radiation, almost perfect from the Big Bang. But if I have hydrogen gas in the universe, I do, because that's what our galaxy is made of, or stars are made of, initially of hydrogen, then the matter actually cools down more rapidly than the radiation. So initially when things are dense, they're very tightly mixed together, nothing happens. But eventually, after time, after again a few 100,000 years, the universe becomes more transparent, the hydrogen becomes atomic, and then the matter cools down. And when the matter is colder than the radiation, you can then see, in principle, an absorption against the background. And you produce these dark absorption lines in the background, which will be traces of the first hydrogen clouds in the universe. All the building blocks of the galaxy, in principle, should be there. Okay, so it sounds incredibly tough, and the reason it's complicated is that if you wait too long, then stars start forming, and they mess things up completely, because they will heat up the gas, etc. So there's a narrow window in time where you can go with your radio telescope to push back to look for this hydrogen. And because this happened a long time ago, this has expanded very much ever since, you're looking for 21 centimeters, but greatly, greatly expanded. In fact, you have to wait until you have to go back so far that it expanded all the way from 21 centimeters to a few meters, basically. And that then gets you far enough back in time to see the maximum effect of the difference between the matter and the radiation. So that's what you're looking for, ideally. So it's a really, really tough experiment to do. Okay. And precisely, you hope to do it because you know exactly what this frequency is that you're looking for. You know it's going to be spread out, expanded by a factor of 50, so it goes from gigahertz down to megahertz, whatever. Okay, very low frequency. It's very, very hard to do, and you probably cannot do it anywhere on the Earth, as I'll explain in a moment. But this is what the future has to be. Okay. Okay, so why do you want to go back so early in the universe? So this just shows you, it's a slightly more technical slide, but it shows you the reason for doing this. So this just is the area here that we measure. This is the strength of the signal you're looking for. This is the area we can measure with a microwave background for large-scale structure from the microwave background. This is what we can ever do with galaxies. And then finally, if we can ever measure these clouds with high precision and very excellent angular resolution, far better than we have over here, then we can actually piece together, this is the power you can hope to get, and this shows you the sort of redshift you have to get to, maybe 50 or something, to measure the best signal you can. This is the strength of the signal you're looking for. Okay, so you have to go back in time if you ever want to get this signal. That's the message, and it's not going to be easy to do. Okay. So to do this, instead of my million patches on the sky, I will need 1,000,000 times more, which sounds incredible. But there are clever ways to do this because you measure frequencies, you can measure different frequencies, and you can slice the universe up into different shells. So that helps a bit. Okay, so ultimately that's what you're going to do, and the precision goes up as this huge number. So going up from 1,000,000 for the microwave background to 1,000,000,000 now, we can in principle get this wonderful factor of 1,000 and look for this ultimate goal. Okay, so that's enough for the theory. I'm now going to talk to you about the practical obstacles to this dream, okay? And you'll see they are truly remarkable, okay? So here is the first problem, okay? This shows you the problems that we have on the Earth when you look at these very low frequencies. And so this is the effect of television and microwave, all microwave links, mobile phones. And so these red divisions are basically channels that are occupied by amateur radio, all sorts of things. And so you cannot do cosmology from the Earth because of all this terrestrial noise, basically. Even if you go to some very quiet place on the Earth, maybe in the middle of the Pacific Ocean or somewhere to try to imagine, away from all the mobile phones, you'll still find that it will be almost impossible. Okay, and this is because you're looking at a frequency where all this is true, 30, 40 megahertz. So there's only one place in the inner solar system which is good enough for this, and that is the far side of the moon, because the moon blocks all this emission from the Earth. So if you can go to the far side of the moon, then you're radio quiet enough to be able to work at these frequencies, which can then take you to the very early universe where you hope to see this signal that comes from before the first galaxies formed, the Dark Ages signal, okay? So that's your best hope. Okay, so So the moon then is the most radio quiet environment in the inner solar system. So we have to go to the moon and go to the backside of the moon. Okay, so what I'm going to tell you now is the future of this as envisaged by our space agencies. So it's interesting that in the US, the space agency there is focused very much on going to Mars. And they are planning ahead for many missions to Mars, eventually manned missions to Mars, maybe in 30 or 40 years. This was a centerpiece of the last Bush administration, actually. It's been up and down ever since, but it's being revived now by the Trump administration, this idea of eventually planning to do something major on Mars. And the moon is just a step in the way. On the other hand, the European Space Agency, which we're still part of, has visions for doing things on the moon. And so I'll show you in a moment pictures of a moon village that is a visionary concept being pioneered by the European Space Agency. And you'll see there are many reasons for doing this. And science at the moment is not one of them, but that I hope could change. Okay. So to start all of this process in going to the moon, the first thing you probably want to do is to put a satellite around the moon. Okay, so this is a proposed satellite, and this would be sort of like a pioneer experiment in terms, in principle. You know, when the satellite goes around the backside of the moon, it can actually have much better sensitivity and then test all these arguments. And there are examples already on the Earth of similar antennae to this, very simple ones in large deserts. Okay. Where they actually are observing the sky. But of course, you need not just one antenna, but many, many to basically cover this wide range of angles on the sky. A single dipole like this basically just has a very crude resolution, although it may be very sensitive. So what is the strategy behind all of this? So the idea is that to get this signal coming from the beginning of the universe, which needs a very fine angular resolution. I mean, the moon itself is about half a degree, 30 arc minutes. You have to be able to resolve with your telescope, you know, a much finer angular scale of a few arc seconds. And that means going from radio telescopes, which at the moment the largest ones are kilometers across, in arrays of telescopes, to ones which are hundreds of times larger to do better, okay? And so that means you want to think about arrays on the moon, on the far side of the moon, of hundreds of kilometers or more. And you can estimate what the bandwidth might have to be in your radio antenna. And that will help you then, because if you have fine enough bandwidth, you can then slice the universe up and look for these structures that I've been talking about. Okay, so the far side of the moon is a unique site for all of this, and it allows you to suddenly go from your million patches on the sky with the microwave background to now huge numbers, 10 billion maybe, just because you're looking at the tiny building blocks that you can't possibly see in the microwave background radiation. It's a totally different technology, totally different window on the universe. And so you can suddenly then get this immense increase in power compared to the microwave background. Okay, so that's the hope. And so you can win by this factor of 1,000. In precision, which is what you want to do, and you can do precision cosmology now 1,000 times better than you can today, and you probably need satellites going around the moon as well as some huge station on the moon to build this array. So let me show you a concept study of what one might be planning to do. Okay, so the idea is to have a lunar rover. Okay, have a huge roll of mylar, or something equivalent to mylar, and in this mylar-like material is embedded all these antennas. These are dipole antennas, hundreds of them, and then this rover would then lay them out, and they'd be connected by coaxial cables, and the rover would lay them out on the surface of the moon. Okay, each one of these might be you know, several hundred meters altogether, and then you would have many thousands of these. Each one would have maybe a 100 or more, maybe 1,000 little antennas on so-called dipole antennas, and you'd have hundreds of these different stations around the backside of the moon, and maybe you would work your way up to 1 million single elements, these things. All that seems feasible in principle. What have we done so far on the ground? I'll tell you what the major problem is in all of this. So this is an example of a telescope under construction. This is actually, most of it's been built already in Canada. This is in British Columbia. And so this is also a collection of, in this case, it's 1,000 different antennae lined up in these cylinders. And they're also very simple telescopes designed also to look for hydrogen. Not quite at these very long wavelengths we're talking about. This would be in the more nearby universe, but again, doing cosmology. And so this actually is the most powerful system in the world in the sense of being able to take all these 1,000 antennas and correlate all the signals together. And so if you ask how many operations do you have to do to just combine all the signals and make a map of the sky, this particular antenna, its world record is, which has the world record, is doing something like 10 to the power of 15. That's 1,000 trillion multiplications every second, okay? Sounds amazing. That's the limit of what you can do with the world's currently most powerful computers, okay? And so this is essentially, that could be applied to experiments like this. So this is where we are at the moment. The problem is that if we want to do this on the moon, with this system I mentioned, well, you have, 1,000 times more antennas, okay? That means you have 1,000 squared more combinations, million. And so, even though you're working at much lower frequency, you have to now do much better by 5 powers of 10, okay, in the future to do this on the moon, to get this computing power. So how on earth can you, that's a huge improvement on current computing constraints, right? How can you make this giant step in computing? Well, there's one interesting thing that takes you in this direction, okay, and that is the immense progress we've had in computing over the past 30, 40, 50 years. It's been incredible. And the basic rule, practical rule, is that our computing power doubles every year, okay? This may seem extraordinary, but this is Moore's law, and it's been plotted here for 120 years. And every year, so this actually starts with the simplest computers, or even non-computers, analytical counting machines, 1900, all the way up to projected to around now, okay? And so it keeps on exponentially growing, okay? And so now this is plotted in computing power per dollar, and if you multiply this by $1 million, you get the 10 to the 20, 10 to the 15th I showed you for the current power of that machine. And you have to now increase this by this factor of nearly 1 million, but you can do that if we now go forward to 2030, it'll keep on going, and bingo, we should be there eventually. So we think that this immense computing effort that you need to do stuff on the moon may not be a great problem if you allow for the future. So in 16 years, our compute power should increase enough by to get doubling every year. That means in 16 years it increases by 100,000 basically. So that's an amazing story. If that should happen, so that's not the problem. So what are we going to do on the moon? So let me tell you about the story for the moon. So here is the moon then, as viewed from the Earth, okay? And we want to go on the far side of the moon, okay? Because that's shielded from all this radio interference on the Earth. Okay, so here is a view on the far side, okay? So it's full of craters, and we're looking basically near the south pole of the moon. And what is interesting about the craters that are actually on the limb of the south pole, it's on the limb of the moon that we can see. And so what is interesting is that these craters are in a zone which is more or less in twilight most of the year. And you can see that the craters have all been given names. And let's consider, say, one of these. And so they've been now mapped by infrared probes a couple of years ago. And so they were mapped and the temperature was measured inside these enormous craters, which are 20 or 30 kilometers across, volcanic craters on the moon. And so one major discovery from this satellite, which thermally imaged these craters on the moon, was that they're actually very cold inside because they're always in shadow, okay? And so, and they found not only that, but they're full of ice as well. So there's a huge supply of water on the moon, and water is the key ingredient you might need to eventually be able to develop a base on the moon. So water is not a problem as long as you're not far away from one of these craters. And inside these craters, they've actually measured the temperature, and you can see so this is in units of Kelvin, And so we are today around here, 300, about 285 maybe. But in the centers of these craters, it's incredibly cold. And throughout the entire year, the thermal imaging show there may be 40 or 50 degrees above absolute zero, which is amazing. And so that makes this site very attractive for doing astronomy, because you want to do infrared astronomy involves cooling down a telescope to really low temperatures, looking at the infrared. And that's how you can see the most red-shifted wavelengths of the universe, how you want to look for the first galaxies. And so it's a great site to build a really big telescope in the future, okay? So astronomers are interested in that. And the one country that's been making so far major efforts to build things on the moon, set things on the moon, is China, actually. So this shows you the lander they had, the moon rover that the Chinese put on in 2013. There's a telescope that they set up on the moon, a robotic telescope, which is running now, observing stars and so forth. The Chinese in next year have a project to send an orbiter around the backside of the moon and bring samples back from the moon and study the backside for eventually building a base there again in the 2030s. But if you want to do something on the moon, you have to start early, and it's a progress, a long progress. So the Chinese have this very much in mind. Okay, but no one knows in detail exactly what they want to do on the moon. All I've heard is that one of the goals of the Chinese Space Agency is to have the first woman on the moon, who'll be a Chinese woman. So that's one of their goals announced, okay? But when that will be, I don't know, but maybe in 5 years, within 5 years almost certainly. Okay, so they're interested in manned flight, and they're developing a base on the moon. So the ESA is very interested too. So there's a new Director General in ESA who been there about a year now, and he has strong interest in developing the idea of going to the moon. What he wants to do, is talked about, is developing a moon village. And so what is the point of this? Well, the idea is that his idea, the ESA concept idea, is that one can do business and tourism. That's, one can find those things being discussed. And so what is the sort of business you might do on the moon? Well, it's mining, basically. So the moon has been bombarded for a long time, for billions of years, by asteroids. There's no atmosphere to protect the moon. And so all of the rare elements in the asteroids accumulate on the surface of the moon. So it's a great place to look for rare materials, rare elements, like titanium or whatever. But there's an even greater prize on the moon. So helium has an isotope called helium-3, which does not exist on the Earth, okay? But you can produce it on the Earth because tritium decays, heavy hydrogen decays into, leaves you a trace of helium-3. So one can make it in small amounts on the Earth. Why is helium-3 so important? Because it is the future for doing nuclear fusion. Okay, if one day we want to have safe nuclear fusion, then helium-3 is one of the key ingredients for a fusion reactor, as opposed to nuclear fission, which is messy and polluting, etc. Now, the moon is a huge source of helium-3 because all the cosmic rays and debris falling from ejected from the sun, basically, mostly cosmic rays, while they impact the moon, they produce helium-3 as one of the byproducts of those impacts. And so the moon, the surface of the moon is probably covered with lots of, we think, must be a great source of helium-3. So if one could go there and mine helium-3, which occurs naturally, one could produce enough of it in great quantities to really revolutionize the future of energy in a century's time. And we're not talking, short time scale here, but this is something for the future. Anyway, so that's and so anyway, so one goes on, and tourism, I should say. Imagine building a resort on the moon. You could have a golf course on the moon. Imagine playing golf on the moon. Gravity's much lower on the moon, be amazing. Right, okay, anyway. So that's not, I'm not sure how much that is a part of current thinking, but so here are some more concepts of a rover on the moon, and again, these are just concepts, okay? So this is, the ESA moon base as it might be in the mid-2030s, okay, with moon rovers and asteroids, okay, around in the vicinity of the south pole of the moon is the current view. Okay, so you can imagine then eventually, and so these buildings are being designed, and they're made from materials that one finds on the moon. So the idea is from the dust, basically, you can compress it in various ways, and you can merge it together to make ideal materials for building. That's one of the ideas being explored at the European Space Agency, and various other ways of one doesn't have to transport everything to the moon from the Earth, which will be expensive. But you can imagine eventually figuring out ways to develop and construct things, build things locally on the moon. So, for this reason, one ought to imagine what could the moon do for science. Okay, so one thing would be using this very cold craters, which are stable, very cold. They're ideal places for building infrared telescopes. But what I think is ultimately even more exciting is to go to the far side of the moon and to lay out these antennae over an area of hundreds of kilometers on the far side of the moon and build a radio telescope, an array of radio telescopes, which will be able to really look back at the beginning of the universe. And so let me show you then, try to summarize for you what this could do. So one would want to start off with a suborbital program using the microwave background mostly, and to start with too. But then you're limited. This is where we are at the moment, actually. You're limited to the magic number of 1 million patches on the sky that you can add together to look for these tiny variations from patch to patch. But you'll never find it because the prediction is not of order 10, it's of order, remember, 0.01. That's what you're looking for. Some number that's 1,000 times smaller than any upper limit we have today from our latest satellite. This is from the Planck satellite, which has just recently finished taking data and has given us wonderful new constraints on cosmology from the microwave background. Okay, and then the next step is to now build telescopes. Again, we're doing this now. We're building enormous telescopes under progress, both on the ground and in space, to survey galaxies. And the idea now is that by doing surveys of billions of galaxies, instead of having just these million patches on the sky in the microwave background, you suddenly have billions of patches. And now you can do much better statistics. Your number n is bigger, so your random variations, the square root of n, are going to be bigger, so you win. But you only win because, unfortunately, you're limited to the square root of the number because of these inevitable random fluctuations by, maybe a factor of 10, which is very good. Maybe, again, if we're lucky, we'll find some hints there of the beginning of the universe. But there's no guarantee, just as there is no guarantee that we'll find these missing hints in the microwave background. Okay, so what we want to do ultimately then is go to the moon. And the reason is then that one can suddenly now, by looking for these clouds, these building blocks of the galaxies, we suddenly go from our billions of galaxies to tens of billions of clouds, which must be there early on before they've all assembled into the galaxies. And then if I have data on billions of these clouds, I can now look for the fluctuations, the variations from cloud to cloud, and suddenly I can now get to the desired territory, getting down more and more. Not quite there yet. We need a second generation, which will be an even larger array on the moon, but why not? Once you get there, you start doing this, and then you can get to the Holy Grail, which is this number of 0.01, and that is just a generic prediction. Okay, one is a generic prediction, but you want to get to for complicated models, but you want to get to 0.01 to really do this problem, and then maybe you'll see patterns in the sky when in this weird thing that I'm calling this parameter, which is exactly where we came from, exactly what the model is that we came from. So that's the great hope. We could finally, by building this giant assembly of telescopes, array of antennae really on the moon, and correlating the signals together, we could do a lot better than we can ever do with anything. So this is a project for the future. Now, there's one real complication with all this, and that is we live in a dirty environment, not just from the radio signals I've talked about, from our mobile phones, internet, all this stuff, but also, and that you can escape to some extent on the moon, but what you can't escape is the Milky Way. So the Milky Way itself is this immense source of of low-frequency radio noise. In fact, radio astronomy began in the backyard of an American astronomer who first built the first radio telescope, a really simple machine, and saw the Milky Way. Okay, that was his major discovery. It was a big surprise at the time, and this is in the 1930s. And so one has to think of clever ways to get around that. But the beautiful thing about this sort of project is that because you're looking for some really, really specific frequency, right, from this atom of hydrogen, which is being excited in a very particular way, then all of these other backgrounds are spread out in frequency. And so we know from experience that we can be very clever and think of ways of beating down the noise in the system. And anyway, so I think it's all very, very promising for the future, but so much needs to be explored that one has to, as is usual with science, you have to begin, step by step. So the first project will be certainly to put a satellite in orbit around the moon and then eventually lay a few things on the surface and then do more and more. Okay, so to summarize, I think one can say now the limit of what we can ever do in understanding our beginnings, cosmology, the origin of the universe, is to try to answer the question, where did we come from? This would be the science on the far side of the moon would be the ultimate probe. We can never, I think, do any better than that. That's as far as we can go, because before then there was basically, before these first clouds, there was nothing visible, and they would have this imprint from the very beginning of the universe on their distribution. And so the idea is to, have this telescope on the moon, which gives a huge improvement. Anything we can do today, and it would be a great complement to other projects involving a base on the moon, both with both business and science and tourism aspects. Why not do science as well? And I think this will enable us to, understand the creation of the universe that we see, and incredibly take us back to as close to the beginning as we can ever get, because when the universe inflated rapidly, that before then there was essentially nothing to see, but we can actually get back to that moment that imprinted this signal on the moon, on our fluctuations, and prove that this theory has a very high probability of being correct. That's about all we can hope to do, but that will be an amazing goal in the next, I would say, century for cosmology. So thank you for listening.